विनय बात हो गई सर से?
सर मैंने कॉल किया था तो शायद किसी मैडम ने उठाया था, तो शी सेड कि 10 मिनट में मैं कर लूं। वो वॉशरूम में थे सर।
अच्छा 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 अच्छा,
तो अभी
ठीक
सर मैं 2-3 मिनट में अभी कर लेता हूँ कॉल फिर से।
हाँ हाँ, ठीक है ठीक है ठीक, गुड।
Good morning, sir.
मॉर्निंग टू यू सर, मॉर्निंग टू यू सर, नमस्कार सर।
Good morning, sir. Good morning.
गुड मॉर्निंग सर। सर आई हैव मेक यू presenter kindly.
No, no, not now.
Anil sir, I have made you the presenter. Please unmute your mic.
मेरा माइक तो अनम्यूट है सर।
नहीं सर, अनिल काकोडकर सर का।
Yeah.
First
I
name.
have unmuted. Can you hear me now?
Yes sir,
Yes, sir.
you are audible sir.
Okay.
Morning to you sir, morning sir.
Morning, morning. How are you, Dr. Garg?
We all are fine sir, we all are fine sir, thank you. How are you sir? How are you sir?
Bas, carrying on.
Your schedule is quite busy sir, I've been observing.
Yeah. Well, जब तक चल रहा है चलेगा.
No, that itself is very motivating to all of us sir.
Yeah.
We'll wait for another 2-3 minutes sir.
Yeah. Suit your convenience.
Yes. How's the corona scene, sir, in Mumbai, sir?
Well, I think not very large as yet, but growing worrisome.
Sir.
So let's hope that you don't get a new wave.
Yes, sir. Yes, sir. Yes, sir. We all are praying that, sir.
Yeah.
Here also it is the same, sir. But
Yeah.
Delhi government probably, we are hearing, sir, they may order the closure of schools, especially the primary schools, sir.
Yeah.
For some time. Could happen.
Yes, lecture school. Very nice.
Good morning, sir. So kindly allow me to start the program.
Yeah, let's start.
Yeah, you may start, Sonia, please.
Thank you, sir. Thank you. Education is not the learning of fact, but the training of mind to think. With these words, I, Dr. Sonia Verma, would like to extend my cordial welcome on behalf of the Director, Dr. A. Garg, and the entire fraternity of KIET Group of Institutions, Delhi-NCR, which has clubbed all of us for this expert talk on relevance of nuclear energy in achieving net zero emissions. I take this opportunity to welcome our guest speaker of the day, Dr. Anil Kakodkar, who is recipient of the Padma Awards. Sir is AICTE Distinguished Chair Professor. More is yet to know. Sir, today our institute is celebrating Thanksgiving Day to express our gratitude to each other. And on this day, we truly express our gratitude to you for accepting our invitation and taking out your precious time. We are honored by your presence, sir. Thank you so
Thank you.
much.
Thank
As
you so much.
simply said, flowers have their own language. This means there is no better way than flowers to express our gratitude to Sir for accepting our invitation to join and honor the talk with his presence. So before starting the session, I take this opportunity to welcome our eminent guest. Sir, on behalf of the entire family, kindly expect our virtual flowers an expression of affection.
Thank you.
Thank you, sir. Now, I take this opportunity to invite Dr. A. Garg, the Director, KIET Group of Institutions, Delhi-NCR, to share the theme of the Distinguished Series and highlights of the academic research activities at KIET. Welcome, sir. Over to you.
Thank you, Dr. Sonia. Very good morning to all of you. On behalf of KIET Group of Institutions, I once again very warmly welcome Padam Shri, Padam Bhushan, Padam Vibhushan, Dr. Anil Kakodkar ji for his second online session with us today. I would like to acknowledge that his previous session on higher education and national development, which was held recently on 26th March, was very, very informative and very enlightening for all of us. One of the key takeaways which I remember was on the user-inspired basic research in higher education institution is lacking in the country. We all are aware that the basic research is there in the institution, but not the user-inspired one. In spite of very high R&D expenditure by the higher education institutions, they are not able to attract the industry investments. Now, the group R&D, which was the term I remember was used by Kakodkar sir, that is the research along with the industry is a big gap in the colleges, and that needs to be bridged on priority. That was a very, very important takeaway and in alignment with the National Education Policy 2020. Today, my special welcome to Dr. Shailesh Tiwari ji, also who is connected with us, who is the director of Krishna Engineering College, our sister institution, and all their faculty members who have joined to us on this platform and who are going to be part of this session today. For all those who could not be present in the previous session and for members of Krishna Engineering College, I'm not able to resist myself from mentioning that Dr. Kakodkar, after earning his post-graduation from Nottingham University in 60s, I think mid-60s or so, his love for the country brought him back to India, and he joined Bhabha Atomic Research Center and has been serving there since that time. He's one of the main architects for creating very strong nuclear footprints for the country. Even the first peaceful Pokhran nuclear explosion, all of us recall that in 1974, was also carried out under his mentorship. If all of you recall, coming to the theme of today's talk, in a recently concluding conference, that is 26th Conference of Parties, popularly known as COP26 in UK, Glasgow, in November 21, our Honorable Prime Minister, he announced that India will achieve net zero emissions by 2070. Now, our Prime Minister also announced that India has to raise its non-fossil energy capacity to 500 gigawatts by 2030. Now, in that context, the nuclear energy utilization as a replacement, as one of the sources for the active energy is very, very important because it has got the smallest carbon footprints. Therefore, the topic of today's session on the relevance of nuclear energy in achieving net zero emissions is very, very timely. And I think it's very, very important topic for all of us. And I'll be very honest in saying that it is still in the academic institutions, we do not talk much about this topic. In fact, they are not aware about this nuclear energies and what kind of a nuclear energy, what are the challenges, what are the research gaps. All that is probably not talked much, and we are not aware. Now, out of my little knowledge, what I see that out of total electricity which is generated by India, not much, maybe I think within 5%, it contributes from the nuclear sources. But in comparison to other countries, I find that the Russia or maybe the US, they have got a contribution of about 20%. France, I heard, is more than 50%. The contribution comes from the nuclear energy. So I'm sure that today's address is going to give us a lot of insight into this very, very important area in which all of us need to work to achieve this target of 2070. And I'm sure with this address, we shall further strengthen our relationships with Dr. Kakodkar, sir. And I'm very confident that sir will continue to be a torchbearer in improving various academic and research processes in the institution. In some way, if both of our institutions like KIET and KEC, if they could contribute in the area of nuclear physics in some way, we would really be fortunate, which will give a lot of exposure to our faculty and students. As mentioned by Dr. Sonia, today we are celebrating Thanksgiving Day. And this day, sir, we have started this year. Only this is the first time. And we thought that we must fix up a day in a year where we should convey our sincere gratitude to our colleagues, team members, leaders, parents, students, recruiters, that is all stakeholders, including the statutory governing bodies and all the eminent people like you, sir, who are connected with us. So my very big thanks to you, sir, that on behalf of my team, I would like to thank you for your contribution. And in about 2 months' time, we are meeting the second time, sir. And we really value your contribution and your association. I also thank all my colleagues on this forum for their continued support in all spheres. And I'm indeed blessed to have such spirited leaders and the team members in the KIT group of institutions. My thanks also to Director KEC and the KEC fraternity for their support. Thank you all. I'm sure today's address is going to be an excellent one, and we all are going to have a lot of learnings and the takeaways from this session. Thank you once again. Over to you, Dr. Sonia.
Thank you, sir. So before opening the session for discussion, let us have the privilege to listen the profile of our today eminent guest speaker, Dr. Anil Kakodkar. For this, I would request Professor Dr. Anil Kumar Elawat, Dean Academics, KIET Group of Institutions, Delhi-NCR, to share the profile of our esteemed guest. Welcome, sir.
Thank you, Dr. Sonia. Thank you very much. Actually, good morning, everyone. As our Honorable Director Sir already said, from this year we are celebrating our first day of Thanksgiving Day. So on behalf of KIET Group of Institution, first of all, I really gratitude to our respected Dr. Anil Kakodkar ji today. Namaskar, sir, and thank you for joining us and blessing our all the participants, students, faculty member, all academic fraternity here. And on behalf of KIET Group of Institution, today, sir, actually in absentia, I actually would like to share, today I met so many faculty and staff members, and they are so much joyful today to thank you the contribution of each other in KIET. So it's a really nice, I think, nice day for the KIET, and the responsibility which is given to me to aware about our today's eminent speaker to our all the listeners. Dr. Anil Kakodkar ji, born on 11th November 1943 and joined Bhabha Atomic Research Center in 1964. He became the director of BARC in the year of 96 and he was the chairman of Atomic Energy Commission and secretary to the Government of India, Department of Atomic Energy during the year 2000 to 2009. He was DAE Homi Bhabha chair professor during January 10 to January 2015 and INAE Satish Dhawan chair of engineering eminence during January 2015 to January 2017 and currently he is AICTE distinguished chair professor. Dr. Kakodkar got his B degree in mechanical engineering from Bombay University in 1963 and MSc in experimental stress analysis from the Nottingham University in 1969. Dr. Kakodkar was amongst the chosen few involved in the first successful peaceful nuclear explosion experiment that India conducted on May 18, 1974 at Pokhran under the great leadership of Srimati Indira Gandhi ji. And later he played a very key role in the series of successful nuclear tests conducted during May 1998, again at Pokhran, again the very eminent leader Sri Atal Bihari Vajpayee ji. India also demonstrated nuclear submarine power pack technology under Sri Kakodkar ji leadership. Notable also are his innovative contributions to human resource development activities, establishment of NICER, National Institute of Science, Education and Research, DI Mumbai, University CBS Center for Basic Science, and HPNI Homi Bhabha National Institute. He has over the years built competent team of highly specialized scientists and engineers in the reactor engineering program, especially nuclear science. He has brought out more than 250 scientific papers and reports on various aspects of his work. Dr. Kakodkar ji was chairman of Solar Energy Corporation in its formative stage. He was also chairman of Inter-University Center for Astronomy and Astrophysics during 2006 to 2012. Chairman Governing Board, Inter-University Accelerator Center, New Delhi, and Chairman Board of Governors of Indian Institute of Technology, Bombay during 2006 and 2015. Actually, I have so much content to read out about Dr. Kakodkar ji, but due to the limitation of the time, I am stopping here my words. Sir, on behalf of KIET Group of Institution, I welcome you in today's this eminent series. Thank you very much, sir, for joining us.
Thank you, sir. Dear all, it is a famous quote that if you want something new, you have to stop doing something old. To enlighten us on the relevance of nuclear energy in achieving net zero emissions is Dr. Kakodkar will be addressing faculty members and students of the institute. We believe that this session will be informative and enlightening for all of us. So now I take this privilege to hand over the session to our guest speaker of the day. Welcome, sir. Over to you.
Thank you. Thank you, Dr. Sonia. Dr. Garg, Director of KIET Group of Institutions, Dr. Alawat, Dr. Tiwari, the entire faculty community of both institutions and dear students. Well, before I begin, let me share my screen. 1 minute. Are you able to see my screen?
Yes,
Yes.
sir.
Okay, I'll make it full screen. It's not become full screen. 1 minute. Yeah, is it full screen now?
Yes, sir.
Okay. So, thank you everybody for this second opportunity to talk to you. In the first lecture, we talked about the linkage between education and national development, and what is it that we need to do, particularly in higher education space, to take national development forward. Energy is one of the important areas uh, which has a very strong bearing on development as a whole. And we are all uh, quite aware of the concerns of climate change, which has come about because of the global warming arising out of greenhouse gas additions, particularly carbon dioxide, and resulting climate change, which may very well threaten the very existence of at least the human species on Earth if we don't manage ourselves properly. And so, as Dr. Garg mentioned, there is a global movement towards elimination of the greenhouse gas emissions and roll back the level of greenhouse gases in the atmosphere uh, to the pre-industrial era. Uh, and in that context, the pledges have been made. The IPCC studies have shown that uh, uh, we must reach net zero by 2050, and also there are other recommendations about how much emission must be rolled back by 2030, and what should be the curve. We'll not get into that. Uh, Now, rolling back uh, CO2 emission to net zero by 2050 uh, is a tall target, particularly for a country like India, simply because we are at the moment very low on the development stage, and so we have a lot of ground to cover in terms of providing adequate energy in per capita terms, and now we have to do that in the context of net zero. So we have to increase the energy supply, and of course we have to decarbonize all our energy supply systems. So this is a great transition, and perhaps India faces the biggest challenge compared to any other country in the world. And so India has announced 2070 as a date for reaching net zero. Uh, let's hope that other countries will reach net zero even much before 2050, so that on an average we will achieve the 2050 net zero target. Now, nuclear energy has a very important role in realizing this target, and that is what is the subject matter of today's talk. So, let me begin. Now, this green energy transition or clean energy transition, I think it is occupying mind space of policymakers and implementers and technologies in a very significant way. But even so, I think it it requires more detailed thought than we have kind of given to this issue. As was said, we have committed to reach net zero emission by 2070. Now, by 2070, our development process is going on, and that's part of that. The per capita energy consumption because there is a correlation between per capita energy consumption and development parameters like human development index. There is also a correlation between per capita energy consumption and, for example, the per capita income or even GDP, which is almost nearly linear relationship. And of course, as energy transition takes place, there are greater efficiencies to be brought in. The energy elasticity keeps on improving. Uh, but uh, by and large, increase energy consumption, economy would improve. Now, so by 2070, one can certainly expect that India can be expected to surpass annual per capita energy consumption level necessary to be on par with the best of the world. In the sense, we expect that the human development index in India would be on par with the very high quality of life enjoyed by advanced countries, represented on this graph by blue triangles. Right now, we are part of the green diamonds where it's marked, India is marked there. And from there, we need to go at least up to this point, because beyond this point, the even if we increase the per capita energy consumption, our human development index would have reached nearly saturated state, and as can be seen, this remains more or less flat. So I think as a minimum, we should reach up to this point if India has aspiration to be on par with the best countries in terms of quality of life, and which I think is a very natural aspirations for all of us to have. Now, threshold per capita energy consumption, taking into account improvements in efficiency as a result of clean energy transition, could be around 1,400 kilogram oil equivalent. Uh, Now, see, if you see this threshold here, which is marked on this is marked as 2,400 kilogram oil uh, per capita. Now, this graph has been drawn on the basis of business as usual. In the sense, the composition of different energy sources as we use. For example, we use electricity, we use oil, we use gas, uh, we use coal. Now, the proportion of these different electricity usage forms uh, in the clean energy transition is likely to change. Today, electricity occupies maybe around 20% of the total energy consumption at the user end. Now, tomorrow, it may occupy a much higher proportion. And also, as a result of this transition, plus special efforts that we are all making towards improving energy efficiency, one can perhaps reach this point in the sense we reach the threshold of highest possible human development index by reaching per capita energy consumption of the order of 1,400 kilogram oil equivalent instead of 2,400 kilogram oil equivalent. Now, on that basis, the total energy that we require to be provided in the country for a stabilized population, because our population also will increase, could be something around 28,000 terawatt hours per year. Now, presently, we are at around 6,580 terawatt hours per year. So, that's a major jump. And if you calculate compound annual growth rate uh, for this transition, 6,580 terawatt hours to 28,000 terawatt hours, between now and 2070, it would work out to something like 4.78 CAGR, which is realizable. For those who have been dealing with this area, they will tell us that this is well within the achievement. So that is what would happen. That is, we'll reach that level of energy consumption for sure, because our economy is growing and the country has both the need for energy and the buying power for that energy. The question is how we will get that total energy, and what will be the share of individual components in that overall energy. Now, obviously, we are talking about green energy transition, and so we are giving naturally a huge emphasis on growth of renewable energy, solar, wind, hydro. Of course, is already there in a significant way, and one would like to see how much we can increase biomass and so on and so forth. So that is a thing which is going on. But if one takes a look at how much renewable energy potential we have in India, and that of course is also technology dependent, in the sense what is the efficiency of photovoltaic systems, whether we are tapping wind at what elevation. If you tap it at a much higher elevation, probably wind uh, energy potential will go up. But having said that, I think as of today, there is a detailed study done by Professor Sukhatme, and which was published in Current Science way back in 2012. And I think it is still nearly up to date. So the total renewable energy potential in the country is around 5,855 terawatt hours. You can notice this is way too short of the 28,000 terawatt hours that we need. Now, of course, there is some revision in those estimates, particularly in the context of biomass, because essentially the non-commercial energy part of biomass, the cow dung, the firewood, which we use in rural kitchens or some such energy supplies, uh, which is not fully accounted for. And of course, there is not adequate data, but it looks like that potential is quite significant. And I'll show you later that it can be as large as 2,500 terawatt hours per year. Even if you add that, you will go to something like 8,300, 8,500 terawatt hours. And we are still very short of the total requirement. Now, in that context, if after accounting for all this, what is left? If you want to achieve your net zero, then in addition to all this renewable energy that we have accounted for, the only other source which will give carbon free energy is nuclear. And that is the importance of nuclear energy. Nuclear energy has an additional importance, and we'll talk about that in a moment. But that importance is with respect to stabilization of grids. See, today, as it is, when the share of renewable energy is not very large, uh, there are issues about the costs that one needs to incur on renewable energy integration in the grids, to stabilize the grids, to create adequate storage in the grid, to have adequate capacity for meeting the peak loads, and so on. And this will keep on rising. And if you want to keep that under check, then you want today, the dispatchable power or base load power is provided by primarily by coal, and coal emits carbon dioxide. So if you want to go away from carbon dioxide, you have to resort to nuclear, and that's another reason why increasing share of nuclear is important. Now, so with that background, this is where what we want to target. Let us look at the energy situation as it exists. So this Sankey diagram in the middle of this figure is drawn from a report, Energy Statistics India 2021. It's published uh, by the government of India every year, and it gives a very granular account of the supply side, the primary commercial energy that is to be supplied into the system, and the energy to be made available at the user end. And of course that data is quite granular, and for to simplify matters I have put these tables. So on the supply side, which is on the left hand side, it talks about the primary energy sources and their relative share at the supply end. And on the right hand side, you have the picture on the user side, energy delivered to user, different users, the industrial users, the residential, agricultural users, transport sector, and we supply energy in different forms. So that also I aggregated, either electrical form or thermal form, because these are the two major groupings in which we need energy. Now it's very clear that uh, you want to reach the transition to net zero, you have to very rapidly scale up clean energy resources. Now, and this is going to take time. And I also told you about this issue of renewable energy integration. And because you have variability in generation, and of course there is also variability in load, so you need a source which can be very rapidly flexed. The powers to be delivered can be altered, and gas is an excellent medium to do so, although gas emits certain amount of carbon dioxide, but it is much less compared to oil, and of course even much more compared to coal. So I think in the interim period we need to emphasize gas economy, which is its share today is quite small, just 6%, as against 20% globally. So that is one message, that between now and 2070 we need to enhance our gas economy share much larger. Come to demand side, today, for example, the share of electricity would be something like 20-25%, as I said, as measured on the demand side. Don't look at it as measured on the supply side, then it will become even less. Now, that share, for example, if you look at the industrial sector, uh, now these numbers in this column are the percentage of the supply side number, that 100% that we have on the supply side here, 100%. Of that, 4.7% goes as electricity for industrial sector, 27% goes as heat, thermal energy for industrial sector, 6.1% goes as electricity for residential and agricultural sector, 11.5% or thereabouts, it goes as thermal energy for residential, cooking and things like that, or also agriculture sector. And about 6.5.8% goes as thermal energy in transport, primarily the internal combustion engines and the like. Now, this we have to make a transition. If you go from today to 2050, it's clear that the share of electricity will go up. For example, we are talking about e-mobility, electric mobility, and which would mean that a good part of IC engines which are driven by hydrocarbon fuels would be taken over by electric mobility. Going forward, maybe also hydrogen mobility. which is likely to be more economical and competitive, particularly for heavy vehicles and heavy vehicles that move in a cross country manner, because e-mobility has range anxiety because of the challenges of battery capacities. Now, similarly, industrial sector, while electricity use may go up, but we may need to provide significant energy in the form of hydrogen, and that would even go further as we move into 2070. Come to residential and agriculture sector. Uh, Now, electricity will of course go up, but can it meet 100% requirement? And that is a doubtful thing. There are, for example, to give an example, there are many aspects of Indian cuisine which cannot be done just by an electric oven. You require flame, and if you require flame, then you require a combustible fuel to burn. Now, we have two possibilities. One, use biofuel in the form of biogas or some liquid biofuel, or you use hydrogen. And it looks to me that for this sector, it would be safer to reserve this sector for biomass and biofuel. And you can still supply clean energy. We have Ujjwala campaign going on to provide clean energy, but that is of fossil origin. We can change that to compressed biogas derived from biomass. We can also change that to uh, the bio CNG, again derived from biomass and the methane percentage enhanced. And to some extent, it could still be the pipe natural gas and LPG as it is today, because if we may not be able to replace it fully. But when you go to 2070, obviously we'll have to change all that to compressed biogas or bio CNG, and eliminate PNG and LPG because they have fossil origin. And as I mentioned, transport, it would become primarily electric and hydrogen and do away with the fossil. So that is the kind of transition one would expect. So the major energy transition in the user segment is expected to be electricity, hydrogen, and bioenergy. And what could be the complexion? To me, it looks that the residential and agriculture, which corresponds to around 32% of the total current energy use, uh, the 32% at the user segment. This would become essentially supplied by electricity, biomass, and I think it has also importance because biomass would lead to decentralized generation. It would also boost rural economy, which is also important from reducing disparities in the country. And we need lot of technologies to deal with that, and we should do that in a technology agnostic way so that we end up in the most efficient technology. The industrial sector, which is the prime share today, around 58% of the current energy use, should transform to electricity plus hydrogen. But I believe the hydrocarbon and coal will still retain their share because I think it may be there are many hard to abate user segments. Uh, and that would mean that if you want to talk about net zero, then we should take care of carbon dioxide by by deploying carbon capture and utilization or carbon capture utilization and sequestration technologies. And as I mentioned, transport sector would essentially transition to electricity and hydrogen. So that is the kind of transition that one expects. I talked about a significant quantity of biomass which is available and which was not previously accounted for, primarily because it was non-commercial energy. And here is a breakdown, and there are references which I have listed from where I have picked this up. And these numbers may vary, but the fact is that there is a significant potential and we must make use of it. Today also it's being made use of, but it affects air quality, lot of smoke and lot of particulates in kitchen. It affects health of women. So we should deploy technology, create, as I said, compressed biogas, and you should have kitchen supplied with clean fuel. That's the thrust which you have started, and that should be become. So we need a create a healthy ecosystem for achieving this. So what are the potential mega trends that we see? While the energy consumption would keep increasing, as I said earlier, because our economy will grow, and it would have to reach at least 4 to 5 times to reach that human development, and that rate would be consistent with the rate at which our economy grows. If the economy grows faster, we will reach there faster. If the economy grows slower, we will reach there slow. Now, while this is so that the total energy would have to, but the clean energy consumption from the present level of consumption would need to increase almost 80 times, and that's the major challenge. And that would be at the rate consistent with what we are doing to reach net zero target. And this is a major technology challenge, because unless we have requisite technologies, while the first one going to 4 to 5 times would be driven by economy, this major increase to 80 times would be essentially dictated by how we are doing in terms of developing and deploying technologies. The increase has to come primarily through renewables, which would include biomass or bioenergy, as I said, and nuclear. Except biomass, all other clean energy sources, they first produce electricity. This is another major feature that we need to recognize. Wind produces electricity first. Solar, particularly solar photovoltaic, produces electricity first. So, quite contrary to using thermal energy to produce electricity, now we are tasked with this challenge of using electricity to produce thermal energy, either by resistive heating or by producing or converting electricity to hydrogen and using hydrogen uh, to produce heat. Now, and if that is the route we need to follow for the entire electricity or entire energy requirements, then the share of electricity would go up very very high, and I'll talk about that in a moment. But there are methods of producing hydrogen even without going through electricity route. For example, instead of photovoltaic, you can have solar thermal, and you can have a furnace which can easily produce 800 or 1000 degrees Celsius temperature. You can also have nuclear reactors, the high temperature nuclear reactors, which can produce that temperature. And then you can use this temperature to split water, thermochemical splitting of water, and produce hydrogen. Some part of hydrogen can also be produced in nuclear reactor by radiolysis. Radiation splits water molecule. And so if you adopt these methods of producing hydrogen in a significant way, then the increase in share of electricity would still take place, but would not be as high as it would be otherwise. For example, the share of electricity would go to 18 to 20% if we are successful in producing hydrogen through thermochemical splitting, as I mentioned earlier. If that does not happen, that share could be as high as 80%. And uh, that in itself is going to be a big challenge, because enhancing electricity sector to that magnitude, particularly, say electric sector coming from renewable or coming from clean energy and going up 80, is a huge big challenge. And I already told you that we'll have to enhance the share of nuclear quite a bit, because available renewable energy can satisfy maybe 30-35% of the total needs. We need an optimum mix of electricity generating systems to assure diversity of supply, because you can't have all eggs in the same basket. There could be issues and the whole thing can lead to an energy system collapse. Optimum peak capacity investments, because as I told you, renewable energy particularly is variable, and also the load is variable. There is a daily load curve. Depending time of the day, the requirement of energy in the system changes. Now, to account for variabilities at both ends, the supply end as well as the demand end, we need to plan for adequate peak capacity. And that peak capacity, if there is not enough base load, that peak capacity would shoot up very much. So it increases investments, and also, as I said, it creates problems with the stability of the grid. Let's move forward. So, just to sort of highlight the economic challenge, even today, the at the current level of variable renewable energy in our system, Indian system, which is around 24.7% installed capacity and 10.7% in terms of generation. The recent report of Forum of Regulators, which is a central electricity authority body, it brings out that surplus stranded capacity. We know enough when there is enough renewable energy, and because renewable energy has must run status, many of the coal plants have to back down. And so there is an investment which does not remain productive. So that is what I mean by stranded capacity. So surplus stranded capacity and resultant costs, that has been estimated at today's level to around 1 rupee 34 paise per unit, and that every energy user has to pay. It's clearly a matter of concern, because this will go up even higher as the percentage share of variable renewable energy increases. Further, there is another study that cost of balancing renewables has been estimated to be in the range of 1 rupee 10 paise per unit by Central Electricity Authority. And when you suddenly lose renewable energy, you have to suddenly bring in other energy sources. I mentioned gas, or could be other. But that balancing requires an additional peak load capacity, which requires you to pay so much. So this would mean that the renewable energy integration in at the present moment itself is costing us a little more than 2 rupees 20 paise or thereabouts. As I said, if we increase its share, the problem would become even bigger. Now, we don't have Indian studies about larger level of renewable energy in the grid, but for example, there was study done by MIT, and also it is incorporated in the OECD report, which shows that as one approaches net zero, a mix relying primarily on nuclear energy is the most cost-effective option to achieve decarbonization target. And you can see the results in the figure that is there. Now, this is a three-axis figure. The two horizontal axes are, one is the carbon emission constraint, the origin being at 0 grams per kilowatt hour and increasing as you come out of origin. And the other horizontal axis is the decarbonization scenario with origin at 100% variable renewable energy. And as you come out of the origin, it is larger share of nuclear, because we are talking about net zero scenario. So now, so if you notice that if you are on the lower plateau, that primarily blue color, Uh, that you realize when either on the net zero axis you are away from 100% renewable energy, you come on that flat portion, and or if you cannot do that and the share of nuclear is low and you're closer to the origin, then you can see there is a big increase, there is a big hill there. And the third axis, vertical axis, is the electricity price, and you can see that goes up quite sharply. And the conclusion of this study is that the minimum average generation cost at low emissions without nuclear could be, in fact, they have estimated for New England region of USA, it could be twice. And for a TBT region of China, it could be 4 times. So you can make your own assessment what it could be for India. And then at that level, optimum tariff level, what is the expected capacity of nuclear in terms of the percentage of peak demand? In New England region of USA, that has been estimated at 60%, and in TBT region of China, that has been estimated at 80%. So that is the importance of having high share of nuclear energy in the net zero scenario, and that is where in India too we obviously need to give much higher emphasis on nuclear energy. Now, so in that background, what are the potential mega trends that one expects to see? From my perspective, I think while total energy consumption, uh, oh sorry, we have already gone through this.
Yeah, we've already seen some.
Yeah, we already seen this. I'm my mistake. I have gone backwards instead of going forward. So the key elements in this transition from to net zero, the key elements of sustainable energy policy, we have to have a policy to facilitate this transition. And the key elements, in my perspective, are the following: electricity, hydrogen, and bioenergy. We have to bring them as key feeders for meeting the energy demand. We must reserve compressed biogas or bio CNG, whichever you look at it, but compressed biogas for cooking energy and bio CNG for running agricultural machinery. Could be tractor, could be pumps, could be the harvesting machinery and so on and so forth. And as against, I told you that totally we have to cover 28,000 terawatt hours. Out of that, 2,500 terawatt hours would get covered by this. We must emphasize decentralized renewables for rural and remote areas through microgrids interconnected to main grids, because that is where we can make best use of renewable energy, and I think it will be more economic to do that. It will also have a better match between the supply of energy and demand for energy. And of course, one should make sure that these are connected with the main grid so that whatever is the mismatch can be covered up by the main grid. Next, we should develop and deploy solar thermal and high temperature nuclear reactors for hydrogen production through thermochemical splitting of water. Because I said this is going to be the largest sector in terms of energy use on the demand side. And I think it makes no sense to first produce electricity and then produce hydrogen, because then they are going through energy transition twice, and the hydrogen will obviously be more expensive. Today, of course, everybody is talking about that route, electrolysis and producing green hydrogen using electrolysis. But that is because we don't have these technologies readily available, whereas electrolysis technologies have started coming into the market. But people have made, in fact, even in India, we have done small scale experiments where production of hydrogen through thermochemical route has in fact has been shown. We have to scale it up to demonstration level to prove technology feasibility, and then commercial level to demonstrate commercial feasibility. But this is the biggest challenge, and I think a lot of R&D is required to be done, both in terms of solar thermal, in terms of high temperature nuclear reactors, and also in terms of utilization of high temperature heat for production of hydrogen. All the three areas are very critical. The next is in terms of augment electricity generation. As I told you, we have to do that. And if we are successful in this high temperature route for hydrogen production, then we can target about 10,000 terawatt hours per year for the electricity generation segment based on an optimum mix of renewable hydro and nuclear. And the shortfall for hydrogen production also, if the thermal route there is a shortfall, then some of it may have to be bridged from here. So that will amount to something like 10,000 terawatt hours per year. So this 28,000 terawatt hours should be broadly, see, these are back of envelope calculations, but I think they may be wrong in terms of the where you are putting your decimal point, but they are not wrong in terms of the block estimate. And so the 28,000 terawatt hours, I think roughly split in terms of 15,000 for production of hydrogen through high temperature route, 10,000 for augmenting electricity system. And mind you, today that 10,000 is only at around 1,600 terawatt hours. So we have to go several times, and of course 2,500 to 3,000 in terms of bioenergy. And for doing all this, as I told you, there will be some share of fossil energy which may remain unavoidable. So we have to also develop carbon capture and utilization technologies to back that up. And that, I think, should be the policy drive, in my view. Going forward, now all these things actually cost money. And just to sort of give you a feel of what kind of monies are involved, uh, let us look at what has happened or what has been happening in other countries. For example, cost of decarbonization of electricity grids. I'm talking about only electricity. Decarbonization of industry segment is yet another thing. In United States, the annual electricity production, the grid size is around 4,000 billion units. Decarbonization of US power grid rapidly will cost $4.5 trillion as per an assessment made by Wood Mackenzie. Look at Germany. Germany grid is even smaller. It is around 6,500 billion units. Now the country is already, there is a great decarbonization plan going on there. They are already spending 580 billion US dollars to overhaul its energy system. Now compare that with India. India's current annual electricity production is around 1,600 billion units. Now we must grow 3 to 4 times larger in BA mode and 6 to 7 times larger in a net zero scenario, as I mentioned. Now 1,600 will become 10,000. Reaching net 1,000, and in fact much larger if we don't make success of high temperature hydrogen production. So for 4,000 billion unit system you require $4.5 trillion. So now these may not be linear, but you can get an idea of the order of magnitude money that is required. And remember, we are talking about reaching $5 trillion economy. So this obviously means that these sums we are talking about are actually much larger than India's GDP. So, it's easy to talk, we will do this, we will do that, but we must have, as engineers, we must have a feel of what we are talking about. We cannot be just romantic about it. We have to have our feet on ground. So, we must keep this factor in view. Now, with that large background and making a case for a rapid increase in nuclear energy, let me come to nuclear energy, and uh, I'll take maybe another 15-20 minutes to finish this presentation. Now we need speedier and cost competitive nuclear capacity addition as we reach approach net zero. And today, of course, we are very proud that we have developed this entire technology on our own. Atmanirbhar Bharat has become an important mission for all of us. In nuclear energy, we have become Atmanirbhar maybe 2 decades ago, as far as technology is concerned. Our problem was availability of uranium. And of course, we now have the civil nuclear cooperation, international civil nuclear. So we have access to uranium. But today, our installed capacity is just around 3% of the total grid, and we want a major share of nuclear. So you can see that there is a very rapid capacity addition necessary. So we need to organize ourselves to be able to do that. What should we do for that purpose? Speed up fleet mode construction of standardized 700 megawatt PHW. We have this 700 megawatt PHWR, which is the cheapest nuclear reactor in the world. Its specific capital cost, dollars per megawatt, is roughly half of the nuclear units built in other countries. And its performance is world class. In fact, some of the units, heavy water reactor units, have made world record of continuous non-stop operation. And of course, there are these reactors have operated non-stop for more than a year, maybe 30-40 times. So they are globally performing reactors. Their capital cost is lower. And if you compare capital cost with for example, the capital cost for producing an X amount of electricity in a year, then the capital cost of this nuclear reactors is in fact cheaper than even solar. Of course, solar can be constructed in very quickly, 1.5 years, 2 years. Nuclear plant takes 7-8 years to construct, and that adds interest during construction. But if you overnight capital cost, you look at, nuclear is cheaper even compared to solar. So we need to bring in speed. That's the main challenge. And today, Government of India has already approved, and the work is going on to construct 10 units of 700 megawatt in fleet mode. So that will add sizable capacity. But looking at this target, the present plans will take our capacity to around 21,000 megawatt installed capacity by 2031 or something like that.
So
Now,
may I ask a small thing, sir, if with your permission, sir?
sorry?
I wanted to just make a request, sir, if possible.
Yeah.
Sir, this nuclear reactors, what does it contain of? I mean, like you mentioned, PHWR.
Okay.
What does it mean? We would like to understand a little more in detail, sir, if possible. What is the composition and what are the other things?
Yeah,
Sir?
so I will explain that in qualitative terms because I haven't got the right slides with me on that. But I'll cover that in a moment.
Okay, sir,
I'll cover that. At least qualitatively, I'll certainly cover that.
Fine.
Right now, I'm making a case for nuclear, and and the major challenges that we have. So, for this rapid capacity in addition, we need just like the fleet of 10 units are under construction right now. According to me, we should take up 3 more fleets for simultaneous construction so that the capacity addition rate goes up. And then, see, there is going to be, we have as a part of civil nuclear cooperation, we have agreements with countries like United States, France, Russia, and those agreements are for setting up light water reactors. And with Russia, as many of you know, we are constructing reactors at Kudankulam. So that part should be speeded up. We should get more reactors with French cooperation, American cooperation, and so on. We should also think in terms of exporting our heavy water reactors, because I think it's a question of overall economy and keeping our industry continuously busy, making them competitive. And so, no, every country, they make some new technology, they partly use it for themselves and partly export out. All countries do that. We should also, of course, our internal demand is high, but we should devote some effort for export. And also, as the coal units get phased out, we need to sort of utilize those sites for locating nuclear reactors, and these large units probably cannot be located there. So develop factory assembled small modular reactors which can be set up in PPP mode at the retiring coal plant sites. So now these pictures you have in this slide, at the top left hand side, this is the picture of the Kaiga atomic power station, where there are there are 4 units. These domes are the reactor containment buildings. 4 units generating 220 megawatts each. On the right hand side top, these are the Kakrapar atomic power station, where you have these 2 units are the old 220 megawatt units. Uh, but this is the place where there are also the larger 700 megawatt units, which I was talking about. So these are the reactors, and those are the cooling towers to dissipate heat. And this is the canal through which the ultimate heat sink for the rejecting the thermal energy is utilized. Now, coming to the reactor, what a reactor is. Now, maybe in the next lecture, although I'm going to talk about the rural development, but I'll bring in 1 or 2 slides on what is the construction of a nuclear reactor. But what you have in this picture, I showed you the pictures of heavy water reactors. I'm showing you here pictures of some more nuclear reactors. For example, on the extreme top left is the picture of a 500 megawatt prototype fast breeder reactor. Next, you have a picture of an advanced heavy water reactor, which is still on paper. Development is complete, so that's why you have an artist impression. And this reactor has been designed to utilize thorium, but also to make sure that there is no impact in public domain. One of the problem is, for example, in Fukushima or earlier in Chernobyl, because of an accident, a lot of displacement had to be carried out of people. That creates trauma. So this reactor has been designed to ensure that there will be no impact in public domain. Next, you have a compact high temperature reactor. I mentioned now for production of hydrogen, you require high temperatures, and this is a reactor based on graphite and beryllium, and can give very high temperature. This is a small prototype, and there is also a design for a larger prototype as a part of this development. But this, as I said, needs to be accelerated, essentially to take care of the green hydrogen needs that we have. And then for the thorium stage, we may need to get into the molten salt reactor, where the heat removal is by way of a molten salt, a mixed nitrate salts, which bring the heat and then you produce steam and then you run the powertrain. And of course, in the ultimate analysis, one also talks about fusion energy, which also is nuclear energy. And right now, there are global efforts. So we have our research and development going on at Institute of Plasma Research at Ahmedabad, Gandhinagar actually. But we are also a equal partner in the global effort in that project called ITER, International Thermonuclear Experimental Reactor, which is a 500 megawatt system to demonstrate net energy release. It is not an electricity producer, but to demonstrate net fusion energy release. And this work is in fairly advanced stage at Cadarache in France. And Indian factories have made a lot of equipment for that. For example, this main cryostat was made in India, shipped to Cadarache and constructed. And the individual parts supplied by different countries, including India, are being assembled in that reactor. And see, the point is, I give emphasis on the 700 megawatt PHWR because that's a technology which is ready, which can be rapidly deployable. And our intention right now is to get rapid capacity addition. Now, but then going forward, we'll need to be able to leverage our thorium resources. All these reactors run on uranium. We also, in fact, we are endowed with thorium, perhaps better than any other country. And you want to utilize thorium, then we have that three-stage nuclear power program, and that we need to leverage. And I'll talk about that in the next lecture. But you can't start a nuclear reactor on thorium, so you have to start with uranium reactors the way we have done, then go to fast reactors, which I mentioned. A 500 megawatt prototype is under commissioning, and then move to thorium stage. So that's a long-term program, but very important from the long-term energy needs, because we're talking about 2050, 2070 as a quick targets in the context of net zero carbon emission. But India's energy requirements are going to be perpetual, and we have to find that. And as you see, renewable energy is available in a perpetual mode, but it is available at that level. So, totally around 8,500 terawatt hours or so. All additional energy has to come from nuclear. And while we may reach 28,000 terawatt hour to reach the maximum human development index, well, we will be in a competitive business world, global business. And as economy grows, we will perhaps require more and more energy. And all that will have to come from nuclear. So I think all this development of nuclear technologies, different nuclear technologies, is extremely important. Now, just to complete what Dr. Garg you asked, conceptually, nuclear energy is produced by way of a fission chain reaction. So, in that fission chain reaction, basically you have a uranium atom which reacts with a neutron, and that splits into two fission fragments. And in this reaction is exothermic, so it produces heat. So the fuel which undergoes this fission, it becomes very hot, and then you pass a coolant over that fuel and heat up. So if you pass water, it becomes steam. If you pass sodium, it becomes hot sodium. If you pass helium, it becomes hot helium. If you pass molten salt, it becomes hot molten salt. And then that you take out and then raise steam, either by water or by sodium or by liquid, all by helium, not liquid, gas helium, or by molten salt. And then that steam is used to run turbines very much the way you run turbine of coal plants. So that's broadly the scheme of things. And then there are, of course, more details. So I'll talk about uh, in the next lecture. I'll devote maybe 25% lecture to this,
Thank
and
you.
25% for the main topic, which I'm going to 75% for that. But that's broadly the approach. And what I want to highlight is the challenge before us. Although I said we are self-reliant, but still, and we have made a workhorse which is globally competitive, but the challenge before us is much larger. So, on one side, you have to have a very rapid deployment of technology which you have already developed, but on the other side, you have to also rapidly develop new technologies that we need to go. And if you do that, then certainly you can actually make a full transition. And the figure on the left hand side bottom is a depiction of that transition, that between solar energy and the energy available on earth, including wind, because they're together. The life on earth is because of sun, or wind on earth blows because of sun. But together we can meet the requirements of energy, we can meet the requirements of carbon, because carbon is an important element. For example, in soil, we must replenish carbon, more particularly organic carbon, for the biomass to grow. So, if you talk about a sustainable system, we have to take all that into account. But the key point is, you want to meet requirement of the country as a whole. You need to uh, give a much larger emphasis to nuclear energy than we are doing today. Now, I did mention about several nuclear reactor technologies, but in addition to nuclear reactor technologies, you need other technologies, and that number is very large, but I have condensed them into a smaller number by grouping them. But the critical technologies for facilitating that transition are, one is, I feel, the ceramic technologies for both fuel cells as well as electrolysis, steam electrolysis, are very important, because you want to electrolyze water for producing steam. You must be able to do that at high temperature, so that the energy required for splitting water is lower, and there is economy there. But that requires the ceramic construction. Today we are all talking about proton exchange membrane based systems, or alkaline fuel cells and things of that kind, that do not go to these temperatures, and that is where you require much higher energy. Among the choices, they may be the best, but that's certainly not the best in terms of an overall energy economy. I did talk about thermochemical splitting of water. Energy storage is going to be very important, both as thermal storage, but also other modes of energy storage. Production of hydrocarbon substitutes using hydrogen and biomass, because petrochemicals has been a big area. So you need feedstocks for supporting plastics or engineered plastics and many other materials which have a lot of significance for supporting human needs. And so there you cannot avoid carbon there. Now, some of it you can do by fossil fuel or fossil materials, and convert them into petrochemicals. But you could also do that leveraging biomass and hydrogen. And in fact, biomass can be used as a feedstock for many of these activities, and that's very important. And then carbon capture, utilization, and sequestration. So these are critical technologies, and we have not done very well on that. We are still in infancy in these. So we may see 70 years or 50 years from now, but they will just pass away. For 75 years of India's independence have already passed away. And how much of technology self-reliance we have, I showed it to you in the last lecture. So you can imagine the crisis. Uh, However, some progress has been made in terms of the carbon capture and utilization. I don't want to spend time on this, but there is some work done by Indian Oil Corporation, Department of Biotechnology. There is a foreign company, Lanzatech, which actually shows a gas phase fermentation to take carbon dioxide from atmosphere or flue gas and convert that into useful materials. Uh, but as I said, this is a tip of the iceberg, and we need to do a lot of work. And the CCU challenge is not as not as simple as it may appear, because the total carbon dioxide that we are talking about is actually 2 to 3 orders of magnitude higher. The total CO2 emission is 2 to 3 orders of magnitude higher as compared to current carbon dioxide use. So how much you will use? There is so much of use does not exist. So you have to find more use, and so sequestration might become important. So while there is a significant scope for increase in CCU, circular economy around carbon and hydrocarbon use would only address the net zero challenge. And so, how can we build circular economy around this? And that's another thing, particularly from a waste-free world. Uh, so, can we leverage carbon dioxide or methane, which is going into the atmosphere, or some such thing which are we consider harmful, to make that feedstock and produce benign material which have some value. And this is actually going against thermodynamics. But nature has been doing that. See, point is, nature's all processes are completely consistent with nature doesn't worry about economy but circularity. And so I think we should think in terms of how to get into circular economy. And that requires, I think, so some of these points are beyond the present realm of technology. You need some very basic thinking, fundamental research as to how you can breach this major challenge. So the field is wide open. The question is, can India be on the forefront? Because these are the topics which are all under research worldwide. If we engage with these challenges and do better in a competitive way, we can in fact be in the forefront. So, and for that, if you recall the previous lecture I gave, you need ecosystem for technology leadership. And as I mentioned last time, we have a lot to do. Sufficient insights for vendor independent autonomous decision making. It should today our decisions are somebody from abroad says I'm going to supply these are the plus points, and we get attracted and buy that. Even for simple things as automobiles, we are doing that. So you have to begin from there. Ability to connect basic research to applications, to proof of concept, to technology, to commercial deployment. And then that means working together of diverse groups with complementary capabilities, the point I stressed last time. And synergistic approach, both top down and bottom up, because you can't, you have a vision and then ask the people from grassroots to use their ideas to bridge that. You can't leave it just, top down, top people do not know the details. So they may have a good vision but falter on details. Bottom people, they have, they can great capability to attend to details, but they should have vision. So they need that synergy between top down and bottom up approach. And that, of course, is a matter for all of us to worry, whether we are in education institution, whether we're in industry, whether we are in government, or whether we are at the policy making levels uh, in the government or in the society. So that's a major challenge. So you would notice that what I said in the last lecture and what I'm saying now, they are all connected to each other. So I hope I have made a case for nuclear energy. Uh, uh, as Dr. Garg mentioned, of course, this lecture didn't cover the details because I thought that will be too much of a detail. But in the next lecture, I would certainly divide 25-75 and cover some details on the construction of a nuclear reactor. I showed you the picture from outside.
Yes,
I'll
sir.
show you some pictures from inside and
Right,
give
sir.
you the detail. Thank
Thank
you
you.
very much.
Thank you so much, sir, for sharing meaningful information on green energy transition challenges we have today to use energy resources with real life example. It was very informative session, sir. Sir, if you permit, may we open the session for discussion?
Sure. Shall I take away my slides?
Yes, sir.
1 minute.
So I request all the listeners to come up with meaningful questions. If you have any queries, you can also write in a chat box.
Yeah, I have a question.
How do I take it out?
You have to unshare, sir, from the next to the leave button, sir, on the left side between mic and leave.
Yeah, here, that cross, no?
Yes.
Stop sharing. Yeah.
Yeah, good afternoon, sir.
Yes. Yeah. Okay. Good afternoon. Let's start question answer.
I'm Srinivasan from the management department. I have a sore throat, so pardon me for not being very clear. I'm not from the technical background nor from the science background, but still have a question. This is an area of interest for me. It was a very nice presentation. It was very lucidly explained to a layman like me also. But there has always been a challenge related to spent nuclear fuel. Disposal of spent nuclear fuel has always been a challenge. And the environmental impact, negative environmental impact of all these spent fuel, dumping of the spent fuel is still an unknown area. And this is a great challenge. If you talk about Fukushima or Chernobyl, Fukushima was a very well fortified plant which was constructed, which was damaged by the tsunami in 2011 and caused a lot of distress to an economy like Japan. So how do you overcome this challenge? Is nuclear power is a sustainable alternate solution, or do we have to still continue with the thermal power, which is causing giving slow poison, but probably not a disaster, going to be proven as a disaster?
Yeah, I think it's an important question, and let me explain this in some detail. See, first about the spent fuel, spent nuclear fuel. Now, there are two strategies to process spent nuclear fuel. The strategies adopted by countries like United States, countries like some European countries, for them, they treat spent nuclear fuel as waste. And so they will first store that spent fuel on the storages at the reactor site, and then afterwards they will condition that, and the plan is to deposit them in repositories, geological repositories. Now, this is where the challenge is, in the sense this has remained an unresolved issue. Unresolved issue in the sense, see, the nuclear fuel has to remain under control, because you don't want, as the time passes, even if you put it in a geological repository, the radioactive materials, they keep on decaying. So supposing, and these half-lives are much longer than the average lifespan of human beings, or also lifespan of institutions. So if you put some material in the repository, over a period of time, the radioactivity will decay out, and then that repository will become a mine of plutonium, which is a risky material. People can just mine that out, separate plutonium, and create a weapon. So it has to remain under control. And the question is, how do you maintain institutional control for something whose life is longer than institutional life? And then of course there are legal architecture has been built and all. But in fact, in one of the International Atomic Energy Agency's meeting on spent nuclear fuel, I was asked to be the chairman of that conference. So, right in my opening remarks in the conference, I boldly said that this approach that you are following has remained an unresolved issue and will remain so for all time to come. And believe me, it was a conference. It was a conference which was of specialists in spent nuclear fuel. They all kept quiet throughout the 3 days of conference. Everybody came to me. Yes, we agree with you. So, which means that is a challenge, and this is exactly what you said. Now, let us look at the composition of nuclear fuel, spent nuclear fuel. The fission products, which primarily cause radioactivity, which decays out faster, uh, is only maybe 2% of the total quantity of material. And then there may be another percent or two of the materials like plutonium or, the higher actinides formed out of uranium, which can produce energy. And of course, some of them can be weapon usable, but they can produce energy because they are heavy elements. Now, countries like India, countries like France, countries like Russia, we don't adopt that policy of treating spent fuel as waste. In fact, in India, we say spent fuel is a resource. I talked about three-stage nuclear program. Our three-stage nuclear program will not be possible unless we reprocess spent fuel, recover plutonium, and convert or use that plutonium to run fast breeder reactor, convert thorium to uranium 233, and so we adopt what is known as closed nuclear fuel cycle. When you adopt closed nuclear fuel cycle, you actually go closer to circular economy, which I mentioned. You know, wealth from waste, as it were. And that is the technology India has been pursuing. India, we have been reprocessing. In fact, the entire PFBR, which you are seeing under commissioning, is running on recovered fuel material from such spent nuclear fuel. And not only that, we have also developed technologies, not only plutonium, but also higher actinides. We can make fuel out of it. And then some fission products like cesium, strontium, we can utilize it, for example, for irradiation of sewage, for irradiation of increasing the half-life of food stocks and things like that. We already made blood irradiator, which are using cesium as a source, cesium immobilized in glass as a source. So we have actually developed industrial scale technologies for doing so. Now, globally, that discourse is there that spent fuel is a problem, but it is not a problem for a country like India because our policy is closed nuclear fuel cycle. That is as far as the spent fuel is concerned. Then there is a question of accidents. Now, of course, accidents are bad and nobody can justify accidents. But nuclear accidents, I'll give a small example. I'll draw analogy from air accidents. If you compare transportation sector and look at where air transport is safer or road transport is safer, uh, the statistics will tell you that air transport is much, much safer compared to road transportation. Per passenger kilometer traveled, the fatalities in air transport are much less compared to road transport. But the trauma that can be caused by an air accident is of a much higher order than the trauma that is caused by road transportation. Because in a road transportation, the maximum number of people who could meet fatality is the number of occupants, which is low. Air transportation, that number is larger. Of course, rail transportation, the number is larger, but on ground it's actually safer, much safer than road transportation. But it is the trauma factor which needs to be distinguished. So actually, nuclear reactors, if you compare fatalities per kilowatt hour energy produced, and you Google it, you will find nuclear energy is among the safest. But the issue is with respect to the trauma. And that trauma, again, I'm not trying to justify one thing or the other, but I'm just trying to analyze this for you. This trauma is because the way way the humanity have understood nuclear or way the humanity is treating nuclear. See, our familiarity with nuclear came with the bombing at Hiroshima and Nagasaki. So we saw huge destruction. And so our mindset tells us that nuclear reactor is equivalent to a bomb and it will cause same destruction. So that's fixed in our mind. Now, and so in our disaster management and all, we adopt very strict policies. Now, I'm not a champion of relaxing those policies in an unmindful way. But the studies done after Fukushima and Chernobyl have shown that because of such large population got displaced without much of a notice, the psychosomatic effects on that population have caused more harm than the radiation. In fact, Fukushima, there is no radiation harm at all as far as the evacuees are concerned. But fact is, we have moved lakhs of people. So this is the challenge, and this needs to be understood this and explained to society people. So I think their concern is quite genuine, and that's why I told you that we designed that advanced heavy water reactor, which will not have impact in public domains. Because if you don't have impact in public domain, then there is no question of that trauma. So that, and the small medium modular reactor which I mentioned is also a step in that direction. So the technology is moving in that direction. Simultaneously, the safety record of these reactors has been improved. So today's reactors, I can say with confidence, are much better. Nobody can say that there will be no accident. But today's reactors are much better compared to what they were earlier. So I hope that answers your questions.
Thank you, sir, for your explanation. Now I request Brijesh sir to come up, please.
Yes, thank you, ma'am. And thank you to Professor Anil Kakodkar, sir, because, sir, firstly, I introduce myself. I am Dr. Brijesh Singh from Electrical Engineering Department, and especially my research domain is power system economics. So I really thanks to you, sir, because you have shown a lot of information related to power industry also. Because whatever the data you have shown in your slides, that may be helpful in future for my research activities. Sir, I have only two major questions related to that. First, as you told, the government of India is also interested to generate the hydrogen as a fuel through nuclear power plant. Right now, most of the researchers, as I seen, they are using the solar thermal energy for the hydrogen production, and maybe in future it will be a business model through nuclear reactors. We will produce the hydrogen as a fuel for the industrial need and the transportation division. But the major challenge is that availability of resource, because most of the reactors are working on the uranium based fuel. So, and as for my knowledge, in database, we have a little bit low grade uranium, availability of little bit low grade uranium in India. So maybe if suppose after 5 or 10 years we will able to incorporate such kind of things. One means like a small kind of reactors for generation of hydrogen as a fuel. Then how we will be match this particular problem, means we will require to import maximum quality uranium from the outside. So and I think as the I means previously I am just when I got the information about this lecture, then I am thinking that the thorium is one of the second resource in India, and it is having a good quality. But the thorium based reactor is under the development. So that this is a new update for me, because you have shown a one type of prototype model, means CAD design of a thorium based reactor. So sir, how we will cater, means is the government, any government having any policy how we will cater the problem of this availability of resources in future?
Yeah. Again, very important question. Uh, See, first about well, India indeed had very modest levels of uranium, and that was the constraint in growth at one stage. Today, both on account of enhanced domestic exploration efforts, as well as now there are no restrictions in terms of commercial access to international market, so we can get uranium in any quantity. Uh, but more importantly, in the context of high temperature reactors actually work much better with thorium. So, in fact, one of the first high temperature reactor which was set up in Germany was in fact based on thorium. And so, as a part of our three-stage nuclear power program, on one side, for electricity production, we may think of using molten salt reactor, which also will work on thorium, and use it for electricity or to some extent hydrogen production. But more importantly, we can have high temperature reactors running on thorium, which, as you correctly observed, we have in plenty in the country, and use that high temperature to carry out uh, production of hydrogen. So that's exactly the development plan. So, and also why we don't want to restrict to only uranium reactors is because, India's energy requirement, as I said earlier, is going to be perpetual. So we must look for more and more energy sources. So to begin with uranium, but look at thorium, and going forward, even fusion energy.
Yes, sir.
So
And sir,
these are all inevitable things.
sir, I have one more question that is little bit related to my research topic right now. That is about the flow batteries. Is there any possibilities, means flow batteries having a good efficiency as compared to all other storage system like lithium ion or the lead acid? So can we integrate the large capacity flow batteries with our nuclear reactors? So by which we can easily store the much amount of the power in those battery system, and then it will be utilized as a capital power plant for the grid also. So is there any
Yeah.
possibility or any kind of research is going on in this direction, sir?
Well, some work is going on. I have seen some work at Karaikudi, the Central Electrical CE or something like the center. It's a CSIR institution.
Yes.
And the flow batteries do have a promise compared to the existing generation of batteries, particularly for storage of larger quantities of energy. But at the moment, they are under development. I haven't seen large scale applications of flow batteries, but there is certainly a lot of promise, and it's a very important research area to be
Yes,
pursued.
because China is going in this direction. He is
Yeah,
doing
no, world over,
research
this is an
in that
important area. I have myself seen some experiments on flow batteries in the lab there at Karaikudi.
Okay, sir. Thank you, sir. Thank you for
Thank
these
you.
valuable information.
Thank you, sir, for giving us your precious time. We owe to you, sir. Now, I would request Dr. Manoj Goyal, Joint Director, KIET Group of Institutions, Delhi NCR, to propose our deepest appreciation. We welcome you, sir.
Sonia, there's another question, if permitted. Dr. Nitin Saxena, probably. Sir, if you permit, a couple of more questions are there.
Yes, sir.
Yeah, go ahead.
Yeah.
Yes, sir. I allow Mike. Nitin, sir, now you can unmute your.
Thank you, ma'am. Thank you.
Yes.
Good afternoon, sir. Sir, regarding nuclear power plant, I have one question. As my one MTech student was working in this field, as we know that nuclear power plant has some no man land, sir, around it. So, is there any government policy? How can we utilize such area near to the nuclear power plant, sir?
Yes. In fact, see, we discussed about the issues in public domain consequent to an accident in a nuclear reactor. So you maintain an exclusion zone between the nuclear reactor and outer public. So around a kilometer radius, land is occupied, and it's used for development of a green belt, because green belt is an easy, good barrier for movement of radioactivity. Now, on one side, as I mentioned, we're talking about eliminating the need for doing so by enhancing the safety of reactors, eliminating impact in public domain. Uh, but that will take some time to be, go through regulatory acceptance. In nuclear reactors, it's not as if I design something and I'm able to implement. You have to prove it to your peers, then you have to go to regulatory agencies, you have to prove it to them, and they just don't go by only paper studies. They want experimental proof. So all that, in fact, for HWR, a good part has been done, but any such forward movement will have to do that kind of research and development. But the direction to go is to, I talked about that trauma, minimize that trauma. So it's no good to say that fatalities are minimum, but if there is an accident where you move some several thousand or a few lakhs of people, it's very bad. So, so that is how that exclusion radius has come in. Now that exclusion radius has also been used for good purpose. Well, one is, of course, you maintain that green belt. So there is always, it's like a forest. So social forestry based activity you can have, which are energy activities. At Kudankulam, we have set up windmills in the green belt. So we are generating, I think, some 10, 12 megawatts of energy we are generating there. Going forward, there is also a plan to leverage biomass arising out of social forestry activities and the energy, and do something about hydrogen and biomass and produce something. And this exclusion radius is a ready-made facility for doing so. But I must say, at the moment, there is nothing of that kind. But uh, at least in my way of looking at it, that's the way we should move. So, so two directions. One, progressively reduce the need for exclusion radius, and that's going to take a long time. It's not going to happen overnight. But in the meantime, leverage that asset for many of the energy studies, which actually become important, as I gave you some examples. So we can move on both these directions. Okay.
Thank you. Thank you.
Yes. Now requesting Professor Ashish to kindly unmute yourself.
Good afternoon, sir. Thank you so much for the wonderful lecture of yours. So my question is, sir, are there any research funding opportunities for higher engineering institutions like us into this area, sir? Because this being very niche area.
Yes. Yes. See, there is an extramural funding scheme of the Department of Atomic Energy called Board of Research in Nuclear Sciences.
Okay.
And that always works on the basis of collaborative studies. So because for you to take up research suo moto may not be very easy, but you can always, for example, there are many institutions which are doing research which are important for nuclear energy, but not necessarily on hardcore nuclear in the sense where radioactivity is involved. But there are several other studies setting up experimental setups, carrying out experiments and things like that. So a lot of such studies can be done. And so the best is you can make a proposal for R&D. And for a better success, I think before you make a proposal, get on with a dialogue with some people in atomic energy, call it BAR, call it NPC, call it IGCAR, wherever, and develop collaborative proposals. And then you send it across to BRNS. And of course, in BRNS, everything goes on competitive process. So there is a strict peer review, just like, DST funding or DBT funding in the same manner. But there is a scheme, and you can, and there are many institutions who are already a part of such R&D.
Oh, right, sir. Thank you so much, sir. Thank you, sir.
Thank you.
Now we believe there are no queries left. Yes, requesting Dr. Manoj Goel, sir, Joint Director, to propose our deepest appreciation. Welcome, sir.
Thank you, ma'am. Good afternoon to all. Dr. Anil Kakodkar ji, recipient of Padma Awards, Distinguished Chair Professor AICTE, Dr. Colonel Amit Garg, Director KIET Group of Institution, Dean Academics, Head of the Departments, faculty members, and my dear students. We really privileged to listen Dr. Anil today once again. Firstly, I, on behalf of KIET Group of Institution family, would like to express my sincere gratitude to Dr. Anil for accepting our invitation and sparing time to take the session once again for the benefit of our faculty and students. Thank you very much, sir.
Thank you.
Sir, your knowledge session on importance of nuclear energy in achieving net zero emissions was very much informative, although the area is new for all of us, but listening from you has given a very good insight about nuclear energy and its use for ensuring the net zero emission, for ensuring uninterrupted power supply to the country. Nuclear power is vital for achieving net zero emissions by ensuring 24/7 energy supply has also demonstrated in the report by International Atomic Energy I think last year or so. So some of the highlight from the session about the green energy transition to comply with India's commitment to reach net zero emissions are, I can make out, sir, sorry if I miss, I cannot, but still I try to be. Nuclear power partnership with renewable energy will be the key to driving emission to net zero, and adopt objective and technology neural framework for the low carbon investment. Also focus, you told about that balancing use of fossil energy by adopting carbon capture and its utilization. Government need to focus to boost public investment and support for private investment in nuclear power, including reactor lifetime extensions as a part of Green Deal and recovery package. Also need to promote for diversified electricity system to mitigate the climate risk to energy infrastructure, ensuring the continuity and quality of electricity services. I submit my gratitude to our Honorable Director, Dr. Colonel Garg, for his ever-ending motivation and support and providing us opportunity to listen the expert like you, sir. Thank you very much, Dr. Vaishali and entire team to organize today's session successfully. Thank you once again, everyone. Thank you.
Thank you. Thank you.
Yes, sir. We believe that any academic event is incomplete without the national anthem of our beloved country. So thus, I would request our technical team to play national anthem. Besides, may I please request you all to stand up for national anthem. Thank you, everyone.
जन गण मन अधिनायक जय हे। भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you once again for joining us
Thank
today.
you.
Thank you.
Thank you.
Thank you, sir.
I-
Thank you once again,
thank
sir.
you.
Thanks.
Thank you. I log out now.
Thank you, sir. Thank you.
Yes, sir. Thank you. Thank you all. Thank you very much.
Thank you, sir.
Thank you, Dr. Manoj. Thank you, Dr. Anil and the team for a very meticulous execution.
Yes.
And very, very happy Thanksgiving Day to all of you once again.
Yeah.
Sir.
Thank you very much,
Thank you.
sir.
Thank you, sir.
My big thanks
Thank
to
you.
you, sir.